Okay, welcome back. Um, yeah, right into it here. Well, just before this. All right, so yeah, lots and lots of stuff. Um, I don't even know how I'm gonna unpack all this for you guys, but anyway, yeah. First of all, I don't know what happened yesterday. I was gonna do another stream. I shut down my computer, and after I shut down my computer, didn't restart. I had to reboot everything, like reinstall fresh everything. But I backed it up this time, so it won't be as long if it happens again. Anyway, yeah, it was unfortunate. But in the meantime, there was lots of developments. World Health Organization update. We're going to go right into that first thing and just kind of skim through some key points. There's a lot of jargon through it, but I picked out a couple of key points that are definitely of interest. They're the most relevant points of the whole of the whole meeting, in my opinion. But yeah, they are very good information for sure. And yeah, basically we're just going to go spiraling out from there. I don't know how it's going to come out, but anyways, we're just going to go. Where am I at? Let's see, I'm not even ready. Alright, so yeah, this here, he's speaking about the window of opportunity. And he's always spoken about the window of opportunity, Dr. Tedros. And he's a very scientific man, very procedurally based person, right? And he states this later on. You'll hear it, and you got to take that into consideration, because right now everything that's being calculated is being calculated at a global assessment level. It's not taking your individual life into account. It is, but you're a drop in the ocean at this point. Although that's how it's being played. All right, that's how everything's balancing right now. They're going on scientific data. They need data to proceed. Blah 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 blah. But we don't have it yet. And this thing is just containment issues, right? Everybody's just trying to contain it as best as we can. But in my opinion, I don't think we're doing the greatest job at that. But anyway, we'll go right into this. And here he's speaking about the window again.
We have a window of opportunity. Maybe you're tired of me saying window of opportunity, but there is a window of opportunity. If you see the number of cases in China and the rest of the world, it's not even comparable. More than 40,000 in China, while in the rest of the world, it's only in the 300s.
Oh, my apologies. My apologies for that.
Realize.
Try to get right back into that. A couple of seconds behind, but yeah, I pushed a button I wasn't supposed to.
You strike hard when the opportunity is there, when the window of opportunity is there. So that's what we are saying to the rest of the world. Let's be serious in using the window of opportunity we have. We shouldn't lose this opportunity. If we lose, we will regret it. And the opportunity was created because of the serious measures that China is taking in Wuhan and the other affected provinces. That is slowing the spread of the virus to the rest of the world. But I don't think this status can stay the same for long. That's why we have to use the current window of opportunity to hit hard and stand in unison to fight this virus in every corner. If we don't, we could have far more cases and far higher costs on our hands. And I don't think anybody wants that. This is a common enemy, and we have to fight it using this window of opportunity and fight it hard. I thank you.
That's some heavy stuff, right? You realize the gravity of the situation he's actually conveying there is, this is, at the moment, unstoppable in China. All right, the rest of the world, China's taking the right actions. So, and well, I shouldn't say right actions. There's no way you can just say those are right, but by those actions, the rest of the world is basically going to be able to have the window to maybe combat this. They're in ground zero right now. It's like a movie. Did you ever see the movie Outbreak? With the monkey and it's just like a weird thing, but it's like, oh, I swear, it's like, when you look at it, it's like, no way. But I knew it for a long time. I did. And I've always been spouting about it and going off, and I got like so many rants and videos, and but it's serious. It is. And it's definitely serious in China. But right now, in the rest of the world, it's just, well, won't go into what he says. Let's go up here. I believe this is about the statistics, about the numbers. So, the accuracy of the reported numbers kind of thing. So let's go. I've only watched this like twice.
Yes, go ahead, please.
Hello, this is Christiana with the German press agency, and it's a question for Dr. Tedros. There are reports today that the National Health Commission in China has changed the reporting rules of cases, meaning that people who are confirmed to be infected with the virus but do not show symptoms are not being counted in the statistics. Have you heard about that, and what is your response?
I don't have that information, but we have regular communication with them, so we will check that, and we have also people on the ground, so we will check and get back to you. Thank you.
Thank you very much. Yes, please, here, and then we will take a couple of more questions from the room here, because we have all journalists who travel to Geneva, so we will give a little bit of a priority to them. Yes, please, go ahead. Make sure the mic is on. It has to be... Yes.
Okay. Thank you, Tarek. Good afternoon.
Very short.
Thank you. Xing from Xinhua News Agency. We've learned that there are also Chinese researchers attending today's forum in a virtual way. So to what extent may the experience of China's health workers and frontline and the collecting and sharing of data by the Chinese researcher help design the roadmap of this research? Thank you.
They actually have first-hand experience and a lot of experience, and surely they will help. And not only that, they will significantly shape the roadmap. But I will ask my other colleagues also to comment on this. But we expect a lot from them.
Just to add.
Yeah, that's just basically how they're going to do the operational kind of side of things with the hospitals and 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 it's not so relevant. I kind of let that play longer than I should. But I thought they were going into something else kind of important there. But what is actually, another good topic in this whole conversation, and this is from the February 4th, so there's like the most recent one. Yeah.
So that's why I don't think it's too late. We have the window of opportunity, and the whole world should really stand in unison to contribute to strengthening the countries with weaker health systems. And that's the answer for now. But that's not just for now, but we have to continue. This is not a few months or a few years of work. It will be many years of work that should be sustained and make our health system as strong as possible. Because we have already seen it. Outbreaks can bring serious upheavals, serious consequences to the world. It's not just a health security issue, or it's not a matter of somebody sick or, the number of people who are dead. It's a matter of political, social, and economic upheavals. It can affect all areas of society. And that's why we have to take it seriously. The world, when it talks about terrorism, and imagine the level of preparation and so on is immense. To be honest, a virus is more powerful in creating political, economic, and social upheaval than any terrorist attack. Believe it or not. I was a foreign minister, have been one of my hat discussing about terrorism and so on, but a virus can have more powerful consequences than any terrorist action. And that's true. And if the world doesn't want to wake up and consider this enemy, virus, as public enemy number one, I don't think we will learn from our lessons.
I don't think
It's
so.
number one enemy, and to the whole world, and to the whole humanity. And that's why we have to do everything to invest in health systems, to invest in preparedness. And that's why I always say that's what wakes me up at night. And it should wake all of us at night. It's the worst enemy you can imagine.
It's the worst enemy you could imagine. Those are heavy words. And saying, like the gravity of the situation, it's not coming through to a lot of people yet. Because they're still waiting on science for actual answers. But they're giving us a heads up, right? Yeah. In not so many words. And there's cause for concern, but to panic, as I should have said as a disclaimer into this whole thing, because it's going to go deep. And I'm going to show you some stuff, and it's going to be probably disturbing, but if you want to know it, it's going to be there. Is it 100% concrete ever, proof? No. But they don't have any concrete proof either. Nobody does at this point, right? And speculation is one thing, but when there's science backing the speculation, becomes a working hypothesis, right? It's as close to a scientific theory as you could get. And I'm not a scientist by any means. I'm not. I don't do science. I actually drive a snowplow. Yeah. So, but this thing has me drawn into it, right? And I grow plants, like marijuana plants. So I studied science to learn about the plants and biology and plant physiology and molecular science, kind of dabbling in it just a little bit, right? So I kind of got a little handle, but I'm by no means an expert, but I can understand certain things enough that I can make some, the average person might not make those little links. I don't know, maybe my little links are short-circuited or something, but it's I hope they are. I do. I smoke enough weed to make sure that they are. So to the next bombshell. Sorry. I'll get it eventually. There. All right. So this has to do with transmission of a, they still don't know how it's being transmitted. Exactly. They know some ways, yes. But do they know all the ways? No. Do they know the full extent of them? No. So it's just they're just figuring this out too, right? Because we're only going on what China was giving us for information, and there's no oversight in their policy or whatever. And we'll get into this whole thing after, but yeah, transmission
potential to wreak havoc. The corona is very different from Ebola. Corona has more potency, virulence. We take it more seriously, but still the position should be, instead of speculation, really to focus at the source, to do everything at the source, slow the spread, stop the spread, invest more in containment, and based on the situation, move into other strategies if necessary. So, meaning we have to be realistic. We have to be calm. But we have to take also serious measures. That's what we advise. And many of the instruments to check it are in our hands. But we can expect, of course, serious things, but let's do whatever we can and contain it. Thank you.
Thank you very much, Dr. Tedros. Let's take one more question from line. John Cohen from Science. John, can you hear us?
I might have queued that up wrong.
I can. Can you hear me?
Well,
Yes? Do you hear me?
Yes.
So can you quickly clarify what the virus name is? You said the disease name. And also, have you received any information from China about the environmental sample?
hold on, I'll try and find that.
And do. And we said, as WHO, containment is possible. So let's not just go into extremes. And you remember, we were actually being attacked for advocating for containment, keeping this virus, Ebola, in DRC and finally finish it. And you remember that. And what happened now? A year and a half, it's contained in DRC. You remember it crossed to Uganda, 3-4 cases, and it was hammered because Uganda was prepared. It's still contained in DRC. There were speculations, there could be speculations. And I don't mind with speculations, but let's have also the balance. What can we do within our hand to really contain this outbreak? And the strategy, by the way, with what we're using now is the same. Hammer the source, hammer the epicenter, slow or prevent the spread of that virus to the rest of the world. And that was exactly what we were trying to do in DRC. So we don't want, as WHO, go into speculations. We prefer actually.
Okay, it's gone. Or I mismarked it maybe. Maybe here. Just one sec, I'll try this.
So that's why when we think about investing in our respective health systems, we should not forget to invest in countries, weaker health systems that need support. So my message again in the middle of this outbreak is the same. We have to invest in preparedness. And preparedness means helping those countries who need a helping hand.
Yes, for sure. Well, I lost my cue on that one, I guess. I don't know where it disappeared to. But yeah, we'll skip to the next one. The other comments were about the healthcare systems.
It's the issue about the use of the window of opportunity. We have a window of opportunity now for the rest of the world. We see what's happening in China in terms of the number of cases and fatality. So if we don't use the window of opportunity we have now, if we don't operate with a sense of urgency, there could be a serious consequence. That's what I meant to say. And I'm reminding the world to use this opportunity to do whatever it can to contain this outbreak. do everything it can. And there is time, because as I said, the number of cases in the rest of the world is less than 400, and there is only one death. That's a window of opportunity. So I'm reminding, there is time, the time is ticking. And time is the essence in this outbreak. And the virus will not sleep and wait. We cannot sleep. So we have to operate with a sense of urgency and with strong political commitment throughout the world. And then we can beat this outbreak. If not, then the other side will happen. So that's why I was reminding this morning, I reminded now, I will continue to remind until the world really takes this seriously, do it with sense of urgency, and believes from the heart that the time is the essence. Time is the essence now. That's what I wanted to say. Thank you.
Thank you very much. Last question, Gunilla, and then we will conclude. Very short, please.
Yes, hello, Gunilla von Hall, Swedish Svenska Dagbladet. I have a question about the British man who obviously infected 11 people while he traveled across the world. What does this tell you, this case? Does it tell you that the virus is changing in any way, it's mutating? And how can countries prepare for these kind of cases and this kind of spread?
So my colleagues will say more, but that's why we're saying time is the essence, because mutation is another issue. Crosses every host, then you know what happens, and everybody knows. So that's why we say time is the essence again, but I would be happy if our colleagues could say, and mutation be one of them.
I really wish we could refrain from personalizing these issues down to individuals who spread disease. This is deeply, deeply unhelpful. These are very unfortunate events in which families and others are wrapped up in, friends and others. There are circumstances that allow disease to transmit. People are not at fault. They are never at fault in this situation. So let's be extremely careful here. It's really, really important that we don't attach unnecessary stigma to this. This is an unfortunate event, and there are circumstances around the way in which disease may have been transmitted, and there may be other clusters like that. This is by no means, and compared to other events, a massive super spreading event. This is an unusual event, and it is a wake-up call, because there may be other circumstances in which this disease can spread like this, and we need to study those circumstances for sure. But it doesn't change our overall assessment.
Okay, so yeah, those are big things, right? You know, the gravity of the situation has changed dramatically. Now, why has that? Well, it was kind of always like an, you know, kind of an urgency, but now it's an urgency. And we can get that, right? He does mention in here that it is airborne, meaning that it can be floating in the air for a certain amount of time. Even they say within a 6-foot range of somebody. And these particles, you know, they're just not sitting there hovering. They're being passed as like people walk by each other and brush by each other. The air currents are carrying this, right? It's not just staying right there. So it's not just a 6-foot radius. It could be up to a little bit more, but that would be the most concentrated area, right? But if you're in an enclosed place, you know, airplane, bus, cruise ship, yeah, it's not good, right? There's so much, right? So now this here, she did say in there that there is bat DNA in it, right? And people are automatically assuming that it came from bats. Well, no, bats, well, it has to come to like an intermediate host to like pass through, right? For whatever, the reason why this is so infectious is either that it did something, like nature did something that it almost never does, right? So there's a whole high probability of everything going on here, right? But it does have bat DNA in it, and the first study also reflected that, but not saying that that was the host, right? Like, it's a lot. It's a lot of DNA and or a lot of science. But you know, this cruise ship, and just to touch on that real quick, like there was another. There's more people infected now, so it's up to, or that wasn't it, or was it? Maybe it was. Maybe I didn't put it out yet, or maybe I didn't click on it yet, but yeah, I'll find it somewhere. Actually, I don't even know where I'm at anymore. Yeah, but they keep rejecting this here ship, the Westerdam. It's out there still floating around. Nobody wants to let it come to port. It's like a big crisis because they've been on there for like, they've been out there at siege, like just chugging around in circles for like 5 days now. Nobody will let them come to port like anywhere along the Asian Pacific. And that's a problem. That's a huge problem. Oh yeah, I guess test or check on this too. So this guy, they were evacuated from the epicenter, and they, well, one of them I guess was initially tested negative, and then yeah. However, on his third test, the man has been found to be positive. So like this stuff is really hard to detect. Very hard. And they don't know a lot about it. They really don't. And the fact that people are getting, like the symptoms are going away is very concerning. And I'll get into that later as well. Because they can get reinfected. Like they might, like it might burn out the body, but it's still in so much close contact and still in them that it somehow does a double infection, or like it's, yeah, but anyway, yeah, that's kind of concerning, really, because he's still contagious. He's not actually cured. He's just symptom free. You know, like he was coughing, had a, you know, fever or whatever, and then he got better. But then there's a second wave. There's like a second wave that comes after this, and they don't know. But yeah, it's crazy. This thing is absolutely epic in the sense of virology. Like if you were like in the world of viruses, this thing is like fucking Thanos. If you know what Thanos is, like with the Avengers and like the guy who's got all the power in the world, yeah. Just because the way that this thing is, yeah, I won't go into it too much yet because I still haven't understood it a whole lot. But here's another case. Yeah, so this guy here, San Diego, test negative, then positive. That's another one. So the person who was among hundreds evacuated to the United States from China was released from San Diego Hospital after testing negative for coronavirus, but was returned to the hospital about a day later after further tests indicated that the person actually had the virus, officials said. So there's another one, right? And here's another one. A woman in her 20s, and this was like around my, like not my place, but in my country, Canada, depending where you're watching this from. But she was from Ontario, and she flew back from Wuhan on January 23rd. No, she didn't. No, it wasn't the 23rd. I guess it was earlier, maybe like a day or two before. But she flew back from China, and then on the 23rd, she started. Oh yes, she was. I smoked too much. Oh my God, my apologies. Okay, so yes, she did arrive in Toronto on January 23rd. So then she didn't have any symptoms, and she was fine, and she took a test, and she was negative. So then 36 hours later, she gets symptoms and goes for testing and tests positive. But this could be multiple things. She could have caught it on the plane from somebody, is what I'm possibly thinking. Because if she tested negative for it right away at that time, it would almost seem, well, and maybe as well, it might not have just been in her system yet, because it's very hard to test, and the tests they are testing negative for this, or it's, you know, even though you might have it, you can still test negative for it, and it's a really hard process to actually do this. Yeah. And this here, so that contributes to it, right? This here, there's a new study out of China. Chinese virus researcher puts the incubation period from 0 to 24 days. So like, you can catch this right away, or it just kind of creeps on you for a long time, and you could have this for a month and like not show any symptoms almost. Or like I said, 24 days, like pretty well a month. Up to. But could it be more? If it's 24, why couldn't it be 34? Like, I don't know. I guess that's kind of a broad statement, but yeah. So they don't really know. That's, you know what I mean? This thing is so, it's like perfect in the sense of a virus. Like, it's stealthy, it's deadly, and it's spreading rapidly, and I'm pretty sure it's mutating like a lot, and we'll get into that and I'll show you why. And it's a good thing, but it can be a bad thing in the event of such like a super spreader. That can be a mutation. Not to say that it is, but it could definitely be of that, right? There's a lot of factors that come into play, especially like how much the person comes in contact with other people, right? People do tend to shed more virus than others, and they don't know why. It's kind of like an anomaly, but they think it has to be like on a genetic mutative level of some kind that allows it to do that. So the WHO said a very long incubation period could reflect a double exposure. Okay, so that's what I meant, like catching it twice. You can get better from this in a sense, to where your body's building up like an immunity to it and responding right, because your body's gonna have a natural defense to attack this. Like, it's once it gets in the system, it'll start trying to attack the virus, the good guys, right? But then maybe you'll get maybe they fend it off a little bit. but your environment that you're in, you know, let's say like you touched a door handle when you were sick, or if you did something, you know, it could live on surfaces. We know that now. Definitely for a few days. They say up to 9, but that's not proven. But let's just say safely it could live on there for a couple of days. And then you get this twice. If you get this twice, it's going to have different, most likely, negative effects in the sense that, yeah, like you become like a super spreader, right? So that's just one expressed gene of a mutation, right? Like there's different, like your gene, the virus is mutating all the time, but it's only going to express certain traits, right? And it's crazy. I'll tell you about it a little bit. I'll try. But I tried to break it down as easy as I could. We're not into that yet. That's a little heavier for later. So yeah, the incubation period, fuck off, I knew I was going to do that. The incubation, yeah, it's great. At present, scientists believe the novel coronavirus has an incubation period, the time between entering the body, the last point it could cause symptoms, around 14 days. And anyone suspected of being infected with the deadly disease is advised to be put under quarantine for 2 weeks, right now in China and beyond. One UK-based expert considered the findings worrying, but suggested that only a very small number of patients were likely to have really long incubation periods. So they are seeing people who have really long incubation periods, but it's just probably spotty, right? It might be 1 or 2 or 3 or 4, but is it more? Do you know what I mean? Like, we don't know how this is even behaving yet. We really don't. But like, they're like, they don't have answers. They don't, and that's and that's just as scary, because it's already being spread, you know, in the West. Like China, I don't think that, you know, unless the virus mutates in a way that it allows it to burn itself out, which it doesn't seem likely at this point, because this thing has been racing for like at least, you know, 3 months, and maybe even longer than that, right? And it's only getting stronger. It's not getting weaker. They predicted this to peak out actually around this time, like 3 weeks ago. They were like, oh well, yeah, no, it's going to burn out in about 3 weeks. Oh no, it's spiking. It's getting higher, especially in China. We're not seeing the big cases anywhere else because it has very, very mild symptoms. And I'll try to keep my train of thought here. Yeah, very mild symptoms. And yeah, this here is life inside Canadian quarantine. Or no, that's not it. Yeah, here it is. So she's on the cruise ship, the princess, or Diamond Princess, and or Princess Diamond, either or one of them. But the cruise ship that's in Japan, that's quarantined, and it's a terrible situation, because if you didn't have this before, you probably had a really good chance of getting this, because just how it's like you can breathe out, and there's like 3,000 people in that ship just breathing in and out 24 hours a day constantly, and it's just being circulated, right? It is mixed with fresh air, but they fucked it up, in my opinion. But anyways, there's going to be a lot of people infected on that ship, and it's going to stress Tokyo, right, or Hong Kong, I should say. It's already stressed them. But anyway, this is her and she didn't even know she had it. Not a clue, but she tested positive, and she's like perfectly well, right? So you contract this thing, and it really does like take a long time before you start showing symptoms, which is scary, right? So, and every case is different. That's another thing. It's like every case that was published from the U.S. so far, they and some out of China, they all have like different symptoms. They're like nobody's like really consistently the same. Everybody's got like a variation of or a combination of some or not some others. So that's really strange. And some people it hits right away, and some people it takes a long time. It's all over the map. Okay, but anyway, we'll get into that later about why it's possibly like that.
Portland, Oregon, Forest Grove, Oregon. There she is, live with us from her hospital bed. Rebecca, I'm just delighted to welcome you to the program, and we can't wait to hear the story you're going to tell. But good morning and welcome.
Good morning, Heather. Thank you for having me on.
Listen, as I look at you, I'm thinking Rebecca Frazier looks pretty well. How are you, Rebecca?
I feel pretty well. I never really had any symptoms like cough, a slight fever when I arrived on Friday to the hospital. Both of those have since resolved. I haven't experienced anything else, so I'm very thankful for that.
Meanwhile, you're still in hospital, and we'll get to the certain, the current conditions in just a second, but take me back to where this whole story began, because we're very intrigued. As I said, we've never spoken to anybody on our program with coronavirus. So were you showing any symptoms? How did you even know you were sick?
Yeah, so basically, once the ship was returning to Tokyo, we learned about that first case from that passenger who disembarked in Hong Kong. As a result, they had the Japanese Health Ministry board our vessel. They did test all of our temperatures that first day. They also passed out a questionnaire in which you would indicate if you were feeling flu-ish or had been to those regions of China that were affected, as well as taking painkillers. My husband and I did mark that we take painkillers, Advil, Tylenol, things of that nature. Mm-hmm. And as a result, we're then additionally targeted for an additional throat swab, which is how I tested positive. My husband tested negative.
Otherwise, you might not have known. I mean, what does it feel like? What did it feel like in your case, this sickness?
I mean, it feels physically, I don't have any symptoms. I would have never known had I not been randomly chosen.
Okay.
Right? And you don't know. That's the scary thing. This thing is silent, and it's very stealthy. It's swift. There's so much speculation and so much unanswered questions from everywhere, and everybody's kind of given like a different play on it. But we're starting to see now from these cruise ships like how infectious this actually is. Now, these are just mild onset symptoms. These are the first wave of symptoms. This thing takes it's different for everybody, right? It's different. And there's no cure for it. Like you might be like, oh, I'll get better and feel like, but you still have it. She's in just an open doctor's room right now. She doesn't have a mask on. And she has it. Like she took a mouth swab. That's what they did. They took a mouth swab, and she's just sitting in there like, maybe she is in isolation, I guess, but I don't know. It's a lot of questions, right? And yeah. So let's go to the numbers. Let's check out this. This is from Center of Disease Control, their update from
The start
today,
of the epidemic.
or I guess yesterday now.
Thanks. Those are both really, really important questions. We absolutely assume that the reported cases are an underestimate. The early exportation of virus to a number of countries was used by mathematical modelers to estimate what the total cases must be. If we knew of 41 cases, but this many countries, we're seeing cases imported among travelers.
So they have no idea, what the numbers are, and at least they're saying that now. Before they were just kind of like dancing around it, but they can't know. There's no way they could know, because most people wouldn't even know they had it until you start getting really sick, and then you go to the hospital, you get tested, and then, most of the time you get better the first time. But this thing like mutates inside you or something, and it just, it's crazy. And everybody has different reactions to it, and that's concerning, super concerning. So mutation, let's check out mutation. What does mutation do? We're going to go a little deeper into the rabbit hole, and I promise you it's going to be a bit to wrap your head around, but if you want to look at it too, I might post the link. But if not, ncbi.nml, or never mind, I don't care. You'll find it if you want to find it. Springer Molecular Life Sciences, you'll find it. Yeah, but first and foremost, I am definitely going to have a smoke, and because I need to before, and just collect my thoughts, mostly because there's just, I haven't said anything because my computer was down, so now it's just all too much. It's all overloaded. My computer is actually finally like legit working good because I had to reinstall it. But anyway, yeah, we'll get right back into this, and after these messages. All right, I am back. Thanks for sticking around if you did. Sorry for the wait, all that kind of stuff. Okay. Oh, where to even start? Okay, so I'm just learning this stuff myself, but it's laid out in a way that, we're going to be able to make some connections here. And I still don't fully understand the principles of these relations or these connections or how they're going to react or all that stuff, but I know there is relations here, and it's very very relevant to this whole thing. So in a mutation, actually before that, I don't even know where to start, but I'm going to try and lay it out as best as I can. The virus that we're dealing with, the one that's circulating around, is an RNA-based virus, which is a ribonucleic acid-based virus. And then you have DNA-based viruses. Okay, DNA is your deoxyribonucleic acid, right? Little bit of science. DNA is double-stranded. RNA is single-stranded. Okay, single-stranded viruses tend to mutate more than double-stranded viruses, which are like DNA, right? So, I don't know how this is going to come in, but I'm going to do my best. So let's go into just reading for a little bit. Okay, so the remarkable capacity of some viruses to adapt to new hosts and environments is highly dependent upon their ability to generate de novo diversity in a short period of time. And de novo diversity means just a new diversity. So more diversity of the virus. So the more diverse it is, the more apt it is to have a sustainable mutagen. Because they do mutate, but they don't really do a whole lot sometimes. But sometimes they mutate and they thrive, and that's not good. So viral mutagen rates are modulated at different levels. So meaning there's a bunch of different variables that determine the mutation rate. There's a whole bunch of things that come into effect that affect the way it mutates, like environment. There's so many factors, right? Just variables. So the mutation rate of an organism is defined as the probability that a change in genetic information is passed to the next generation. Meaning, when somebody gets this and it infects their body and they give it to somebody else, that is the next generation of a virus. Even when a virus replicates in a cell and copies itself and comes to the next point where it's making a next generation of itself in the cell as well. But then as it spreads onto a human, it's passing on those genetics. Like if you were, same thing with having a baby, right? You put two together, you get a little bit of both in the end, right? So it's kind of the same thing. What else? What else is really vital? Okay, so higher mutation rates lead to higher genetic diversity, except in special cases. It is not possible to infer mutation rates directly observed population mutation frequencies, meaning a whole lot of jargon, but there is, when you get a whole lot of diversity in the virus, except in special cases, the observed, you don't see the outside effects of it, right? You don't see what it's doing outside your body. Like, let's say you like runny nose or sneeze, or like, external things that you can see, right? So it's not really observed in the population. So similarly, mutation rates should not be confused with molecular evolutionary rates, and that plays a factor because there's different mutations on different levels. One is a biochemical mutation, and one is a genetic mutation, meaning like it's a mutation of, like on a DNA, RNA based, like if it was like a computer program, it would be like, you do something to the programming to make a difference. That would be like I can't explain it, but they're different. One's and the biological one is one that happens between mutations that happen with the biological processes in your body, and other factors, right? So it's a lot. Yes, it is. It's a lot. But I'm getting to a point eventually. But you kind of have to have a little rundown of how this virus thing and the mutation and why it's so important right now. So knowledge of the processes underlying viral mutation rates has implications for understanding and manipulating drug resistance, immune escape, vaccination, pathogenesis, and the emergence of new diseases. So, in clinics, the importance of viral mutation rates can be illustrated in the history of anti-HIV treatment. The nucleoside along the AZT, it's just a drug that they use to try to fight HIV when they first started breaking out. Unfortunately, the appearance of the drug-resistant variants rapidly frustrated this monotherapy, meaning that they tried this therapy, but the virus grew an immunity to it, right away. It adapted, and basically it didn't work. So HIV-1, okay, and this is very important. HIV-1 is the same protein that was used, or is found in the new virus, because there was a paper that came out, and the paper stated it's got the HIV-1 genome in it. So why is that relevant to here? Well, the HIV genome just happens to be one of the most experimented ways of superhuman, giving a virus superhuman strength. This protein affects how strong it is, and how many hosts it can attach to, and how viable it is, how vicious it can be. This specific protein, HIV-1. And when I was reading this at first, I was just trying to get some information on genetic, how this thing mutates. So I dug this article up and I started reading, and as I got down here, I was like, what the fuck? I started reading it and I was like, what the fuck? And if you hadn't seen the old article, well, it's not an old article, but this is the first published paper, and not published. onto the internet, published, like, so the people could see. For the wise, for the world, right? But it's not officially published in like a medical journal or anything yet. But the fact that this here, and I seen that, and then I seen that in this paper, and how they use that in laboratory settings to actually make shit worse because it's such a fucking perfect protein to do that. I will tell you about it. And this paper has this virus has this protein in it. And they were like, and it's the glycoprotein 120. And it's the fucking, it's, I could be wrong. But I think I just really found 100% fucking evidence. Or at least, it's not fact, but it's at least evidence. It's a direct link. I'll probably get fucking offed here. It'll be like fucking Secret Service agents knocking down my fucking door, and I'll be getting taken off to a quarantine camp or fucking. I was okay. So let's go back into this paper, the other paper. So this is why I'm. Down here. Okay, see? Okay, wait. This is a visual representation of the virus. These here points, where it is at, is where the most activity takes place for host recognition. And then you got these HIV proteins on there. Glycoprotein 120s, but it's the proteins. It's not HIV, it's the protein in the HIV strain. It's the glycoprotein, they call it 120 because there's probably a lot of them. But it's a glycoprotein, and that's what it is, and it's attached to this point to increase infectivity and increase mutation. But you can't predict how mutation is going to react. There's no way. It's a fucking roll of the infinite dice. It really is. There's no way to tell. And it's not meant to freak anybody out. And, but it just so happens I found this in this article. So let's keep going through this article before I get whacked by like fucking Men in Black or something. But anyways, okay. So this here was a nucleoside that was used for approved drug use for fighting HIV. This is back whenever it first started breaking out, when we were just starting to figure out about it, right? So, when they tried the drug on it, HIV-1, this specific protein was responsible for being the defense and causing it to rapidly mutate. And there's so much, and I'll never be able to unpack it. But I'll do my best. Oh my fuck. So, the subsequent success of highly active antiretroviral therapy did not reside on merely increasing drug potency, but mainly in combining different drugs, including AZT, such that the chances of resistance mutations were minimized. So they threw like a bunch of different virus-fighting drugs at it, but it was more like a range, so as not to cause it to mute, because if you just throw one at it, it has a chance it's going to attack that all at once. But if you keep adding onto it and piling onto it, the virus is going to have a hard time keeping up with with all that workload, right? So it can't mutate and get stronger as fast, I guess. So what's key here is that HIV-1 is a fast mutating virus and produces every possible single base substitution, like within every day. That's why when you have AIDS or HIV, it doesn't go away. Because it's very good at fighting off anything, like, you know, anything that's gonna, like, it's very hard to fight this. Obviously, we haven't found a way to do it yet, but this it's the protein, right? And it produces every possible single base substitution. So meaning it has such a more better chance at producing a viable mutated virus, so that the virus will actually thrive. Mutations happen all the time, but they usually die off because they're mutants and they just can't survive. They're usually missing something, or got double to something, or there's something wrong with it genetically or something, right? So, but usually they just die off. But the more that you have mutating, the higher probability you'll have that, you know, it's the same thing as like if you buy lottery tickets. If you buy 20,000 lottery tickets, you'll have a better chance of winning than if you bought one, right? So it's the same thing here, right? It's giving it a higher probability to mutate and get a mutation that will actually thrive and live and survive. And when that happens, that's not good, okay? And that's what this virus is doing, because it does have that protein in it. And it is capable of mutating so many times. And that's why I think they're having such a hard time diagnosing this and seeing different symptoms in everybody. Because when everybody gets this, it's just doing all this weird shit. It's not the same. It's like it's trying to pick a perfect mutant. And if you get that, and they give that to somebody, well then, that's it. That it would. This here is something that they can still treat you with, but a mutation would be, I don't know. We don't know what it would do, but it would be very bad. It would be absolutely worse. You could guarantee it could cause you to become a fucking zombie. And theoretically, it could. Like, you could just have a ridiculously high fever and, you know, just be like in a zombie state or something, right? You know, not necessarily meaning that you're going to eat people, but unless I guess you were very hungry and there was nothing else to eat, because it would be an apocalypse. So, you know, I'm going out to left field. Let's get back to science. So, RNA viruses versus DNA viruses. Okay, this is big because, like as I was saying earlier, DNA's got 2 strands and RNA's got 1. But then there's another substrand of RNA. I don't know, but anyway. I'll try to wrap it. I'll try to get it out as best as I can. So, coding. Okay. Just 1 second here, because it just goes through a whole bunch of like what different ones are. So, viruses are the biological systems with the wildest variation in mutation rates. The largest differences being found between RNA and DNA viruses. A summary of mutation rates for different viruses, blah blah blah, table 1. So as discussed in previous work, the reliability of some of these rates is compromised by several sources of the estimation error and bias. Despite these uncertainties, it can be inferred that viral mutation rates roughly range between a lot. So, yeah, and that's not really the point I was going to get to. So, first, yeah, and I don't know a whole lot of this, but the polymerase of a vast majority of RNA viruses lack 3 exonuclease proofreading activity, and hence are more error prone than DNA viruses. So RNA viruses are usually bad at replicating themselves. When they replicate, they don't complete, the strand or the code, right? So they don't get to thrive. They don't live. And that's one of the downfalls of RNA. But if you were to, let's say, add HIV-1 proteins into this spot where the proofreading activity happens, it would be less prone to error, which means that it would be more prone to produce a mutagen. So yeah, I know it's a lot. The exception, now here's the big one, and I fucking shit when I seen this. The exception to this rule is provided by coronaviruses family. And this is when I just put it all together. I was just like, what? If you were going to make a virus, this is exactly what you would do. You would use a coronavirus RNA-based virus, and then you would put in these inserts so that it could actually be, more effective, more capable of mutating, more. It's just, but, so anyway, it's not proven. I'm not saying this is 100%, but if in fact that's how you were going to do it, this is how you would do it, and this is why you would do it that way. This is why you would use a coronavirus and link it to an HIV-1 protein. Because it goes on here, and I will say that the protein is, in effect, an amplifier. So it makes it stronger. And that's why the paper, when it came out, it said there's an uncanny similarity between HIV strains. Okay? And where these strains are is where the points of activity of the actual virus to, like, the hands of the virus. You just gave brass knuckles to a fucking virus, essentially, right? Like, it had hands before, but now it's got, like, brass knuckles. And that's, you amplified it, right? So, but it's not necessarily brass knuckles. What these proteins do is help in cell recognition. So meaning that it has a better chance of being, hey, I know what this is, clunk, and just latching onto it and being able to program that cell is what it would do. It will inject the RNA message into the cell so that it will make a copy of itself. It will turn that cell into a copy of itself, and then it just copies and copies and copies. Then there's transcriptive copies, and then there's transcriptive are like variable, I think, and then there's like stamp copies, which are like, it's like a photocopy, just keeps making the same one, but then there's other ones that make a little bit different, so those are the ones that can mutate. If that makes any sense at all. I know it's so deep. That's what she said. Okay, no, I didn't say that. It has been speculated. Okay, no, I'm not on the right place. But yeah, The reason why, okay, it has these proteins, right? This is the HIV glycoprotein 120, okay? And that's exactly the same protein that they use in laboratory settings to make things worse. This paper that I'm reading right now is saying the reason why they use that protein specifically is because it's so viable on like every level in most viruses. So it just fits. The pieces fit because the HIV strain has every possible genetic code. It produces every possible genetic sequence that it would just line up, you know, like eventually, you know. Anyways, it's a lot. Yes, I know. Just wait. It's not even the half of it. Okay. So let's go back. First, the polymerases. Okay, let's go, and just so everybody and even I can take a double check on polymerase. It's an enzyme, okay, which brings about the formation of a particular polymer. What is a polymer? You say? Come on, polymer. I swear. I'm going to try and make it so like everybody can understand it. So, at least. A substance that has molecular structure consisting chiefly or entirely of a large number of similar units bonded together. Many synthetic organic materials such as plastics and resins are polymers. Okay, so why does that matter? Okay, so polymerase. These are enzymes. Oh my god, I can't even think now. So first, the polymerase, they're enzymes, right? And of a vast majority of RNA viruses lack the proofreading activity, right? So if you give them the proofreading activity, which I will show you why the HIV-1 protein is a proofreading, it makes it so that it has a better idea of recognizing its host, so it can thrive. And then, but the weird thing about this coronavirus is the protein for the HIV is it's super resistant to like, and it's anything that you throw at it as a therapy kind of thing, it will react, and it's just like, you know, it will build a defense very fast to it. Okay, so where are we at here? Back up. At present, a combination of therapies are the only effective way to treat fast mutating viruses. And if you look at the case files from these patients, it shows like what they're using, and they're using a wide variety of antiviral things and all kinds of just a wide variety is what they're doing. So it's fast mutating. That's like but that's not a good thing. It's not. And why I think this is uncanny, let's just say, that the fact that this HIV-1 protein is used for, okay, viruses with smaller genomes tend to mutate faster, which is, you know, because RNA is single-stranded, it will mutate faster. So single-stranded viruses, okay? We'll go through this really quick, maybe not too quick. Single-stranded DNA viruses tend to mutate faster than double-stranded DNA viruses. Although the difference is based on work with as biotrophacies, as no mutation rate estimates have ever been obtained from eukaryotic single-strain DNA viruses. Within RNA viruses, there is no obvious difference in mutation rate, except in the coronavirus. That's the exception. And it is in here somewhere, lost in the words. It is a lot, and I'm just trying to still unpack it in my brain here for you. So here we are here. Polymerase fidelity variants. So fidelity meaning infectious, meaning stronger. So this is what would affect them. So the fidelity is the ability to incorporate the correct base and exclude incorrect bases from the active site during DNA synthesis is a primary mutation rate determinant. So if you have the correct bases from this activation site, which is where these HIV proteins are at, they align with these sites, and they're all the glycoproteins, right? And except this one here is the amino acid, and there's one that's different. Now I'm not a scientist, and I'm still trying to put this together in my head, and I'm just waiting for Men in Black to come smash my door down, because I don't know if I actually found something that actually relates conclusively that this is not fucking natural. It definitely relates to it. Is it conclusive? No. Does it definitely relate to it? Yes. Okay, hold on here. I just gotta read some stuff really quick. And it is a lot. It is. Okay. Template-dependent effects on mutation rates. Okay. Template meaning being able to replicate itself, right? So the fidelity, or the strength of a given polymerase varies according to certain template properties. It is well known that misalignments at homeopathic or homeopolymeric runs can cause frame shift mutations on base substitutions. Sequence context may influence the fidelity of HIV-1RT by modulating enzyme binding and dissociation. Okay, so it's going to it's going to help the binding spot, right? Or so I think that's how it's reading anyway. So also RNA secondary structures have been shown to promote template switching in a process that does not lead to new mutations but produces recombinant viruses. So it's actually making viruses that are going to be able to thrive. In recent work, we found RNA structure can also modulate the fidelity of HIV-1RT. So RNA structure can also modulate the fidelity. So an RNA structure, which is a coronavirus, right? That's an RNA structured virus, will increase the strength of this particular protein. So they will work together. They will actually, if you were designing something, you would go bloop, bloop, because it would be more infectious. And the reason why they do this to make things more infectious is to study how that works and how things mutate on an extreme level, right? And then find out how things work. You got to go ahead to go backwards in like microbiology, in a sense, like we're virus or virology. So let's read that again. In recent work, we found that RNA structure can also modulate the fidelity of HIV-1 RT. So that's a replicating template, RT. Shuttle vectors are systems in which most or all sequences except essential CIS-acting elements or long-term repeats have been removed from the viral genome. So if these are removed, and this is what they're doing, they're removing them and documenting on it, right? But they're using the HIV-1 insert with this, right? So it's something that is, it's compatible, I guess, with the coronavirus, but it wouldn't be in nature because they have to actually insert this right now. Nature can't do this, so they have to use these proteins because these proteins are going to help the virus mutate and live. If you can't let the virus live, that's it's just not going to work. You can't study it. But if you can super, make it super strong, it will definitely thrive, right? And the mutation rate, there's a lot in here, and I don't really understand a lot of it. I don't. But the fact that this protein is linked directly to this paper, the exact one, the glycoprotein 120, and it's the same one that they use in medical research for discovering how things mutate. Okay, anyways, okay. Targeted hypermutation in viruses. Okay. The finding that HIV-1 has a reduced mutation rate in the genome region encoding the outermost domains of the GP120 envelope protein reveals that an uncoupling between mutation rate and genetic diversity, as these domains are the most viable regions of the HIV genome, mainly as a consequence of immune pressure. So this region, it is mutating in a sense, but I don't know. I can't even still figure it out. But the region that they're talking about is the active region, right? So where the information is going to get passed from the virus, when it bumps into your cell, if it bumps into it, if it can attach to it and it hits this active area, it will try to recognize that cell. And if it recognizes it, it will send its encoding into that cell and replicate it. Okay, so for targeted hypermutation, okay, so So this indicates that the HIV-1 has not evolved to the ability to target mutagen to regions where they are more likely to need for adaptation. A possible evolutionary explanation for the GP120 V1, V5, that's just a location in a genetic sequence. So there's a cold spot that some, and these here are genetic sequences, these APBO, that's like your chromosomes kind of thing. But the C, that is one that will infect humans. But anyways, So, a possible evolutionary explanation for the GP120 cold spot is that some human-driven mutations favored by immune pressure during HIV-1 evolutionary history resulted in the loss of certain human targets, leading to the subsequent reduction in mutation rate. So if it loses things, it's not going to mutate as fast, right? It's not going to be viable, and it will burn itself out. It will mutate to the point where it can't, because a virus has to copy itself, and it's like transferring data from like your hard drive or like to your phone or to like to like a oh my god a zip drive. You know what I mean? USB. It's like the same thing. If when you're transferring information, it's got to transfer that, and certain information it can get corrupted in the process of that transfer, right? It happens a lot more for genetic level than it does for a computer, but it's the same kind of process, right? You can still have corrupt files that come over, and it's still the same thing. Okay, so if it is making too many corrupt files, it's not going to be able to sustain itself, which is, conversely not a good thing for the virus. So, but there is a way you can fix that so that it's making very accurate copies of itself with the help of certain proteins. So, similarly, strong selection at the protein level may have favored amino acid replacements within the region at the cost of disrupting pre-existing RNA secondary structures. As a consequence, these RNA structural changes would have modified replication fidelity. So, yeah, meaning that it's going to make it stronger, right? But what the link is here, I'm not sure of a whole lot of it, but I know the link is that this specific genome, the one that's in this paper, is being used to make, it's being used in a laboratory setting to make a virus more viable. And so that it can recognize more hosts. Yeah, it's just a lot. So interplays between mutation and recombination. I'm just going to read straight through this, or try my best without interrupting. So, diversity generating retroelements have not been described in eukaryotic viruses. So eukaryotic meaning that they're going to infect mammals and birds and blah 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 blah. Where did I stop? I told you I wasn't going to stop, but I did. But these viruses can use other mechanisms of mutational targeting that involves recombination. The inverted terminal repeats of vacina virus contain 10 to 100 base repeated sequence motifs known to experience frequent unequal crossover events and rapid changes in copy number. Recombination has been shown to promote this rapid production of genetic diversity in other genome regions of the vacina, or the vaccina. So anyways, this protein is a central effector of innate antiviral immunity and induces translocational shutoff, modifies protein, basically modifies the protein's inner workings, alters the RNA stability, and includes yeah, I don't know where I got there. But what it's doing is it's saying that this here protein is enhancing the virus. So experimental evidence supporting and joint effects of recombination and mutation rates and viral adaptivity has recently obtained using poliovirus polymerase mutants that individually after replication fidelity or recombination rate. So in other recent work, a low fidelity variant of subsidus virus was found to exhibit increased recombination. This variant showed low fitness and greater tendency to accumulate effective interfacing particles, mutant viruses with large deletions that depend on and interfere with the wild type infection. Therefore, it appears that high mutagen recombination rates enhance viral adaptability, but only up to a certain point, both which process contribute to the accumulation of so a virus can mutate up to a certain point, but it's good, and then it's bad for the virus for its fidelity, or for its strength to survive, really, is what it means. So, but that whole thing, basically, what I was getting at is that they were using these proteins. So using this system, we recently characterized the distribution of mutations along the HIV-1 envelope. We found that 1 kb region encompassing the V1, V5 loops of the GP1P envelope protein accumulated approximately 3 times fewer mutations than other regions of the HIV-1 genome. So the HIV-1 genome being, it's going to be, it has more. And being that it is an HIV, it creates like a perfect strand without, it's going to create a better copy, right? That's why they're using it. So it's like using a better hard drive or a better flash drive to transfer your data. It's the same thing. It's making a connection to the system. That's what basically this is. It's the hands that are like, but like you just gave the hands brass knuckles, because these proteins, these glycoprotein 120, insert one, HIV-1 glycoprotein. It's the exact same protein they were using in that lab experiment to boost up this fucking polio virus. And they made it like a ridiculous amount more infectious and more viable. But this here amino acid is different from this. And the amino acid, which was the polyprotease, that was the enzyme, but basically turns into an amino acid. I don't know a whole lot about it. But the fact that the genome source country subtype was, here's one from Thailand, here's one from Kenya, and there's from India. So this was the protein acquired from this particular strand of HIV in this region, because there's different types of HIV, like small little variants, right? And that's what a mutagen is, right? Small little variants. But they know enough that they're like, it's got a fingerprint on it, and they're like, hey, this one came from the HIV strand in Thailand. This one came from the one in Kenya. This one came from the one in India. And this one came from the one in India. But the novel inserts are part of receptor binding site. So the binding site, meaning that's the activity site, right? And why you would put these HIV proteins in this binding site is so that it has a better opportunity to recognize the cell and to replicate itself at a more efficient rate. That's what this protein does. It is like super fucking, it just super juiced it. Could it have happened in nature? Yes, it could have. Penguins could have flied before they didn't have feathers. Maybe. I don't know. It could have. But there's a lot of speculation. And this is a link. I was like, okay, there's a reason. Like, it's weird why they would use this protein, and I kind of realized, like, but then I wasn't even searching for that information. I was just reading up on mutations. And this paper is on mutations and what affects mutations and the mechanism of viral mutation. So they were using this in a lab setting with the HIV-1 protein GP, like the glycoprotein 120, the same one that's in this. Okay, they were using this protein to induce hypermutation and fidelity and genetic diversity and evolution. Those are key words, but those key words are exactly what makes a virus very unpredictable and much more likely to have a viable mutation that survives. And if that happens, we don't know what happens. Maybe it did happen. Maybe that's what this is. But the fact that these proteins are used are in this when they have to actually add these proteins because they're so well fit for this type of work, but they don't exist in nature. So they have to create them using this protein. If it existed in nature, they would just study that virus. They wouldn't go through all the work to put this fucking protein in there to make a virus more infectious if the protein was already in a natural virus that was more infectious. No. Right? Am I wrong? I don't know the whole makeup of it, but it definitely links. You know, they use the HIV-1 protein at the binding site, at the activity site. Let's see if I can find. There was more information. I don't know if I can search. Can I search on this? I don't know. Damn it. But anyway, yeah. But they use this exact same protein for a scientific experiment in what we're looking at in this paper. The exact same proteins, the glycoprotein 120. And why is that so special? Because that is exactly, it's like the communication center. It's the what's going to recognize. You know what I mean? It's like giving the virus eyes so it can see, you know, except like now it's got like fucking supervision. And anything that it's going to recognize a cell more often than not, because usually they don't recognize it. It's harder for the virus to get hold and go. But the better the virus can recognize a cell, and the better it can put that information into the cell. Because what it's got to do first is it's got to bump into that cell and be like, hey, oh, what's this? Oh, I think I can fit here. And then it'll try to put the message in, right? It'll recognize the cell first. And then it'll try to put the message in. And basically what the message is this encoding. It's basically sex on a cellular level, and it's going to replicate a cell of its own. Coronavirus. Excuse me. No, it's just joking. That's not funny. Don't joke about that. But yeah. Oh, there's just so much connecting this. There really is, and I don't think I'm crazy, because I might have not unraveled that as best as I possibly could, but yeah, I'm just kind of drifting off here for a minute. Yeah, I think, well, basically, that's almost all I wanted to get out of that, I guess, if there was anything that came out of that, was the fact that they're using an RNA-based virus, right? So an RNA-based virus would actually be the best virus to use, because it's a single-strand virus. You wouldn't use a double-strand virus. A single-strand virus has more chance to mutate and create a viable, it makes better copies of itself. It does. But the problem is that coronavirus has a hard time usually recognizing the cells to get in, right? But if you, in essence, give it like supervision and a way to interact with the cell by giving it this specific protein, which they're using in these studies. Let's just see. Host-encoded mutation rate modifiers in RNA reverse transcripting virus. So there are 7 human genome which have been shown to also edit retro elements and other viruses, including hepatitis B virus. Editing is strongly dependent on sequence context. The major determinant of editing for human is the base 1, which is like the HIV 1, right? It's the base 1. That's why it's the HIV 1. They name it 1 because it's the base protein. And that is the major determinant of editing for human. And these APEB, that's just genetic code of some kind. So, but what we're going to get here out of this is that it's a major determinant is the base 1 protein, right? That's going to be your biggest determinant, and that's where it's at. That's what our HIV 1 is. It's the base protein, right? And it's weird. So, in recent work, we have estimated the relative contributions of hosts and their viral replication to the total HIV mutation rate in vivo. I'm not sure what that really means, but we found the majority of mutations, 98%, are produced by APOBCs, and this elevates the HIV-1 mutation rate by 40-fold above the replication error rate, making HIV the fastest mutating virus described so far. In many cases, hypermutation leads to loss of infectivity and hence effectivity. It exerts its antiviral action. So meaning like if the virus mutates too much, it'll kill itself off in a sense, because it can be a good thing for a virus to mutate for a virus, or it can be a bad thing in the wrong proportions, right? But if the proportions are proportionate, then the mutations, it can keep thriving. It won't kill itself off. But what's important here is that so when they found in the HIV-1 editing of complementary DNA strand structures, so GG to AG, so when they edited this, these protein structures went from a whatever type of protein these are, a GG, to an AG, and or a GA to an AA mutations in the genomic RNA. So it was just by editing this, the strand produces this instead of this, and this instead of this, and that's what they produced in an RNA structure, in the genomic RNA. And coronavirus is an RNA structure, and I'm still trying to put all this together. But by editing this, it makes these different mutations. So in recent work, we have estimated the relative contributions of hosts of host AP. So that's just like a human host. That's like it can infect a human or a mammal. So we have estimated the relative contributions of host specific, let's say, and the viral replicating ability to the total HIV mutation rate in vivo. I don't know, I guess that's some kind of virus they're studying or something. We found that the vast majority of mutations are produced by these specific genes that elevates the HIV mutation rate by 40-fold. Making HIV the fastest mutating virus described so far. So they're using these inserts because it can defend itself. If it can't mutate and adapt to, like, let's say, treatments and therapies, it won't survive. But if it can adapt to those therapies and those treatments, you just made it stronger, and now that one, that particular strain, if it gets passed on to somebody, well, now it's stronger. If you're, it does. That's sometimes it'll kill it off, but if you don't kill it off and it becomes resistant to it, well, it's going to get stronger, right? And then what are you going to give to it? So you can't really give nothing to it, and then eventually it does. It takes over the host, right? Okay. But basically, the whole thing is that they're using this HIV-1 glycoprotein 120, the exact same one that is in the paper here. And the protein is inserted in areas where these activity centers are, where the recognition happens. So So this basically is an amino acid. So this amino acid protein of HIV is involved in host membrane binding, which means host membrane binding, it's attaching to the membrane of the cell. Packaging of the virus and for the formation of virus-like particles. GP120 plays a crucial role in recognizing the host cell by binding the primary receptor CD4 This binding induces structural rearrangements in GP120, creating high affinity binding site. So it was put there. I don't give a fuck, because if the scientists are using it in this situation to give these viruses a higher fidelity and a higher infectious rate so that they can study them, why wouldn't they use the same? Well, of course they would use the glycoprotein 120 amino acid from the HIV virus, because that particular protein is a super fucking, it's got like, it is, that particular protein makes it recognize the cell so much better. That's why whenever you get HIV, you're infected. You have that. It's the same thing as this here. You have it for good kind of thing, right? You don't get rid of it. So would be in turn a sought after characteristic if you were to go do something like this, because you can only attach certain it's not like you can just take any protein and just throw it on this recognition site so that it can basically replicate itself. There's only certain sites on a virus. Each there's, you know, it's the same as us, you know, we don't got arms coming out of our ears or our forehead, you know, we only got so many arms and our legs, and that's where they are, right? These are our sources for interaction with our environment. It's the same thing as a virus, but you're giving the virus like super sticky fingers to like hold on, like, you know what I mean, and it's able to recognize the cell. So that's why they use this protein, because it not only is it very good at recognizing cells, it's very good at making defenses and mutations, and also it's very good at being at recognizing, at being compatible with most viruses, especially the coronaviruses, because it's an RNA type virus, and it has a lot. I don't know a whole lot about it, but I'm just trying to put together the little links about why they would, you know, they're using this protein in a laboratory setting because it works with most viruses. It fits, the puzzle fits. You can make it a super virus, and they did this here. And it's the same one, the exact same protein, glycoprotein 120. And they say it in this paper. They're like, why would that be there? And they would know right away, like, you know, like, okay. And it says this binding induces structural rearrangements, creating a high affinity binding site. So high affinity, do you want to see what affinity means? Oh my god. Come on. Affinity, high affinity. It has a high or spontaneous or natural liking. Yeah, a similarity of characteristics suggesting a relationship. So it has a better, you know, way of developing a relationship with your cell, right? It has a high affinity binding site. So that's exactly why they would use these inserts at these exact fucking points. You know, because that doesn't happen in nature. And the bat DNA, why? Why bats? Because bats are mammals. And it's used as an intermediate so it can infect humans. You need you need mammal DNA in a virus in order for it to affect mammals. But you need I just lost my thought there. Spaced. But yeah, you need the mammal DNA in order for it to affect a mammal. A mammal, like a bat virus, would not affect a lizard, or a snake. It's a reptile. If it made a jump from the bat to the snake, or if it made a jump from the snake to the bat to the human, that's a possibility. But that's almost like no, just can't happen. There'd be like 1,000 chance, no, because they don't fit. The pieces don't fit. They just don't. Nature isn't that far along on the evolutionary stage of viruses. Like, we have a big database of viruses already, and we know them, we study them, and we kind of know where everything's kind of at on an evolutionary scale. It's not possible at this moment. And that's what they say in this report. Evolutionary analysis. So, it has been speculated that the CoV is a variant of coronavirus derived from an animal source which got transmitted to humans. So, it's been speculated. Okay? Considering the change of specificity for host, we decided to study the sequence's glycoprotein. So the glycoprotein 120. So the change for specificity for host, which means that basically this protein is going to enhance it so that it can see or even attach to multiple hosts. Like even birds, or let's say, or even cattle or farming animals, right? So they decided to study this here, the protein, and they knew there was something off about it because it was like, this seems like it's a little different. So thus a change in the proteins can be reflected as a change in host specificity of the virus. To know the alterations in S protein gene of nCoV and its consequences in structural rearrangements, we performed an analysis with respect to all other viruses. And it is revealed that S virus protein has evolved with the closest significant diversity from SARS. So the closest that they can relate it to on an evolutionary scale is the SARS one, right? So to our surprise, these sequence insertions were not only absent. So yeah, if I was a scientist, I could probably figure this out better, but all I know is that they, and then here it says, we were not only, these proteins were not only absent of SARS, but were also not observed in any other protein in the Rna, which means any family of coronavirus. So these weren't in any other coronavirus. And this is startling, as it is quite unlikely for a virus to have acquired such unique insertions naturally in a short duration of time. Meaning, like, on the evolutionary scale of things, they know that this isn't fitting right. Like, maybe a long time down the road, maybe after a lot of mutations, a lot of drifting, like genetic drifting, that's all comes into play, right? Everything. And it's just not at that time. And the insertions are these binding proteins that help. So you know what I mean? It's I don't know, it's a lot. I know that. It is a lot. It is. But the thing to take away from it is, in this laboratory experiment, in this published paper, it's actually published. This article has been cited by other articles, published on 2016, July 8th. And I was really blown away once I seen that they were using these proteins, the same glycoprotein 120. And they were saying, well, the reason why they use that is because it's a great candidate, because it just fits so well with most viruses, but it doesn't happen in nature. So they needed to actually do this. And they did this one on polio and a couple of other ones. Yeah, and it's a lot, right? And is it concrete? No, but is it other scientific evidence that says that they use these things they use this other strain in laboratory setting to make viruses stronger? Yes, because it's right here. They actually edited this protein into these tests, whatever they're testing, the mutation rates. Yeah, that's what it was all about. I was actually looking for mutation rates and how mutation kind of really happens, and I found this study on mutations, and they're using HIV-1 glycoprotein 120 in their work to make a virus more stronger. The finding that HIV-1 has reduced mutation rate in the genome region encoding outermost domains of the GP120 envelope protein reveals an uncoupling between mutation rate and genetic diversity, as these domains are most variable regions of the genome. Oh, excuse me. Yeah. It's a lot, but they're using this exact protein right here, right? In this experiment. And here you got the exact same protein in this virus. The exact same one, the one that they're talking about. Why is that there? Why is that there? But you got other laboratories using it in their work to make viruses stronger, better, super viruses. And that's what they're doing. So it's in here. The virus, or the protein that they use in laboratory settings to make viruses, the exact same fucking one, dude. The exact same one. With all that jargon, I wish I could have just come out and said that, and it probably would have been easier, but then at least you can see the data behind it, right? The shit is there, and this is what they use. And these proteins, about right where they are, it's they were put there They were put there. Because if they happened in nature, they would study that virus replicating. But no, it doesn't happen in nature. So they had to insert it. And whatever this other amino acid does, I don't know. I don't know what any of them do. But I know that I know that the glycoprotein has to do with cell recognition and cell vitality and its rate to, or its ability to infect and replicate and sustain and mutate. Because if a virus doesn't mutate, you can just use something on it and it will kill it off. Mutations have to happen in order for it to be able to defend an immunity to it. Same as our bodies, right? We develop immunity to certain things, all right, over time. You know, it's the same thing. But yeah, that's a lot, right? And the whole thing that got me thinking about this was the update from the World Health Organization. The last comment that he said about the super spreader, and that if this thing mutates, if it has a sustainable mutation, or if it already has, or you know, a viable mutation is not a good thing. It really isn't. But why would they use it, right? For host and cell recognition. They took this RNA-based virus, which has, you know, a better chance of making copies of itself when it does mutate, right? And then you add this protein on it to have it be able to infect a cell 40 times more likely, or whoever knows how many more times likely, but obviously if it's on there, it's going to be more likely to infect your cell. So it has a better chance of making a mutagen, and I don't know if it's that or what, but that's kind of what I got out of the deal, that this thing is mutating so fast that they can't keep up to it. They're trying different things, but it's just not working. And that's thanks to combinations of a whole lot of different, whatever. If you're like a microbiologist, or if you're a virologist, or whoever that studies these things and does these things, you would know, like, how, you know, what's going to be more viable in the end, right? To work with if you were going to make like a super virus. And this protein, this specific protein, is the best one. Glycoprotein. The same one that's in this study that everybody kind of flipped out about and was like, oh my god, it's a biological weapon. Well, it doesn't necessarily mean it's a weapon, but it does necessarily mean that it's not natural. Because why would you use these exact proteins, or why would these exact proteins, I should say, show up in something natural when they have to actually force it in a laboratory setting? Yeah, it's a lot, right? Yeah, but they're using that exact one for this test, for mutating viruses. This is a paper on cellular and molecular mechanisms of viral mutation. mechanisms. And they're using this exact protein in their studies as the exact protein that's in here. Exact one. Why are they doing that? Well, because that's just what you would use if you were going to make a virus, because it has to be able to sustain itself and all the pieces have to fit. You just can't throw anything at it. It's got to be, but the HIV-1 protein, it's the protein, it's the GP, that's the glycoprotein. It's that protein that interacts with the binding site and the virus. It's like the intermediate, it's like the messenger, right? And the recognizer, it's everything. It's the doorman and the fucking bellboy and room service and fucking everything. It is. It's like, it's that intermediate piece that needs to be there for the cell to make a connection. And I was like, what the hell? And I was reading all these things, and I was going through all these case files, just interestingly, not like because I'm a doctor or nothing. I'm just actually interested in this. And some of the things that I picked out of it is that everybody's displaying a little bit of different symptoms. And in this report, there's, how do you say, expressed traits of the virus, and then there's ones that you don't see, but the expressed traits like coughing, pneumonia, high fever, all these things that are associated with it, those are expressed on the outside, right? We can see them. But on the inside, there's other things going on that we don't see. But it's mutating. And that's why I think, I don't know, that's what I'm kind of putting together, is that because everybody's kind of having different symptoms, it's the same strand, but it's mutating a little different than everybody else. And it's looking for the right, it's like, that's what a virus's number one goal is, to sustain itself. But it can't sustain itself if it doesn't adapt. But if it adapts too much, it goes too far and it'll burn itself out. But if it adapts just right, it can create a whole new virus, a mutant that is able to survive and thrive. And when that happens, that's really freaking bad. All I'm saying, it's like, we have no idea. It would be, especially in this case, if this thing mutates, because it's so new, right? The novel coronavirus, it's novel means like new, that's all it means. But this is already so far along on the evolutionary scale already in terms of where it should be, that if it mutates, it could create like a whole race of different like people, like a whole classification of like if it sustains itself, like, is what I mean. It could literally like mutate your cellular level to a point where it creates you as a mutant, right? We don't know, but it's jumping. This is already so far on the evolutionary scale, like where it should be. And that's why they say there's uncanny similarity of new inserts, novel, which just means new. Uncanny and similarity of new inserts. Spike protein to HIV-1. So this protein, and then they add this to it. And then when these two get together, that makes the virus so much more stronger and viable And that's why it's spreading so fast. Because this thing wasn't made by nature. Fuck no. But I think I don't know if it was really, I don't think. But you never know what you could think, right? Actually, I do think too much. I got kicked. They don't like me talking about this stuff, I guess. Wow. That was intense. Is it going? It's going again. Oh my fuck. I mean, I just got... Somebody obviously... Somebody obviously did that. My whole internet just fucking dropped. Wow. But anyway, I guess you're not supposed to talk about anything. I can't believe that. They don't like you talking about stuff, do they? You know, you find out stuff. They don't like that. I wouldn't be surprised to get some fucking men in black at my door. Or whoever. Talk about anything. I can't believe that. They don't like it's just so coincidence. Everything just, you know, I lost connection. My router went down and everything. They don't like that. And then I had to re-fucking... Wow. Men in black at my door. Coincidence? Could have been. Right in the middle of, I don't know. I've never had my router drop like that before, ever. It's just so coincidence. Everything just... But yeah. Okay, I'm going to shut down this stream and I'm going to leave it at there. I'm going to start another one up again right after this one. I'm going to use some encrypting software. It takes up more computer RAM and shit, but I don't know. Am I being overcautious? Yeah. I already got a VPN up and running, so like it's but I'm just gonna put some extra on it. And yeah. So process that. I don't know. Maybe this video will disappear if you never seen it, I don't know. But yeah, that was fucking weird. I've never seen my router do that ever, and my router been through some stuff, you know what I mean? So, yeah. We'll get back into it, sub and do all that kind of good stuff. I'm gonna smoke a joint and hopefully not get killed. Somebody fucking show up my door and just fucking take me to the quarantine zone. Alright, anyways, I'll be back soon.